We've already established that a long straight wire carrying a current is going to have a magnetic field around it, and by now you're pretty comfortable with figuring out the direction. Again, thumb in the direction of the current, direction that the fingers curl around is going to be the direction of the magnetic field, so kind of counterclockwise around the page here. Let's talk about the magnitude of this magnetic field. Turns out magnetic field in Teslas is going to be equal to this new constant, which is simply the permeability of free space, 4 pi times 10 to the minus 7th, multiplied by the current in amps, and then divided by 2 pi, and then this is going to be the radius away from the from the wire. So if we were to kind of picture the wire going into the page here, I point my thumb in the direction and figure out that it's going to be curling around in that direction, so that's going to be the direction of my magnetic field, and the field strength is going to depend on how far away from the wire I am. Now, what would happen if we had two parallel wires that are both carrying current? Well, you can get some practice using the right-hand rule, figuring out the direction of the magnetic field for each, and say, hey, this is just like two magnets interacting. There's going to be forces. What we can then do is say, well, we know that the magnetic field is going to be related as such, where now here I've got some distance between the wires, that's simply my radius. And then we know that the magnetic fields will actually be 90 degrees apart, so we can say that the force is going to be the current times the length times the magnetic field. Sine of the angle is just 1. And then take that guy, plug it in right here, and what we're left with is this equation right here. That's going to give us the force on pretty much either wire. It's going to be permeability of free space, current 1, current 2, distance of separation squared, and then the length. Now, very often what you're going to see is that the length is going to move over here, so maybe we'll move that length over there and scratch it off right here and talk about a force per unit length. Say I'll talk about 5 newtons per meter or something like that. This concept of force between two parallel wires actually becomes more and more important as we shrink to smaller and smaller and smaller devices. Think about the forces if these wires were like a nanometer apart or something like that. And pretty much direction is going to matter, and I'm going to leave it up to you to convince yourself using the right-hand rule that parallel currents are going to attract and currents going in opposite directions are going to repel. Please do make sure that you're good to go with the right-hand rule, because it just keeps on coming back and coming back with these magnetic fields. Now we know that a coil of wires, or a current-carrying wire, is going to produce a magnetic field. What would happen if we were to take it and then wrap it upon itself many times? It creates what we would call a solenoid. And essentially what we're going to do is you can do the right-hand rule and convince yourself that the magnetic field is going to be pointing in that direction. And then every loop that we have is actually going to magnify that magnetic field. It's going to add to it. And we're going to get a nice uniform looking magnetic field through the center of this solenoid. It's actually going to look a lot like a bar magnet. You could kind of picture this guy right here simply being a magnet with the north end over here. You've got the magnetic field lines kind of wrapping around, and the south end over there. How much magnetic field? Well, that's going to be related to several properties. The magnetic field in Tesla is going to be equal to the permeability of free space. That's going to be the number of turns that this guy has, multiplied by the current in amps, and divided by the length. Solenoids are actually particularly useful. We can use them as an electromagnet. For example, think of what they would use in a junkyard to pick up a pile of scrap. They want to be able to turn that magnet on and off. So what they can do is they could dump it down into a pile of metal, turn the magnet on, run some current through this wire, move it over to where you want, set the current equal to 0, and the magnetic field will release the metal. And just in case, another practical application is going to be in your doorbell. If you've ever wondered how that thing works, well, here we're going to have an open circuit with a switch, solenoid right there, and just kind of an iron rod on a spring. You go ahead and you close the circuit when you press on the doorbell. It attracts the iron rod, goes over and strikes the bell, and now you know you have visitors. Now, how do we go about driving some of these expressions for magnetic fields that we've been talking about? Turns out that we use something called Amperes Law, which is actually fairly similar to Gauss's law. And what Amperes Law says is if you take a closed loop and say, what is the total current flowing through that loop, it's actually going to be related. So if I've got some current flowing right here, and I make kind of a closed loop, kind of as it's shown right here, then the magnetic field multiplied by the length of the loop is going to be equal to mu naught multiplied by the current enclosed. Now in general, we're not going to take any weird jagged paths like that. We're going to take nice, smooth, easy paths to calculate, as I'll show you on the next slide. So let's kind of take a look at just a current carrying wire. Let's say, alright, let's apply Amperes Law. So I'm going to choose my path to be kind of this circle going around the wire right here, and I'm going to have some radius r away from the wire. Now B is simply going to be the magnetic field. The path length is going to be the circumference of the circle, so it's going to be B multiplied by 2 pi r is going to be equal to mu naught, and I enclosed is just going to be the current I. You can kind of see that B is going to be equal to mu naught I divided by 2 pi multiplied by r, which is the equation that I simply gave you earlier. You can also kind of follow the example in the book and convince yourself that you can do this for the solenoid example as well. Now let's kind of consider if we have a closed loop inside of a magnetic field. So here we're going to have a kind of a magnetic field going in this direction right here. You can kind of convince yourself that there's going to be no force on these two ends. However, there's going to be a force on this wire that's going to be opposite to the force on that wire. So kind of what we have here is we have no net force, but we do have some torque that's being applied to this loop. We can go ahead and calculate this. Remember that a torque is going to be equal to a force multiplied by a distance. Turns out that it's going to be related to essentially the number of coils that this loop has. It's going to be multiplied by the current in area, or current in amperes, the area of this loop, the magnetic field in Teslas, and the angle that the magnetic field is going to make with the area vector. Occasionally, this NIA term might be shortened to what they call a magnetic dipole moment, but I wouldn't worry too much about that. Practical applications of the torque is going to be something like an electric motor. Consider having a magnetic field running from north to south right here, and we have some loop, that we attach to a shaft, and we say, hey, we're going to connect this to a potential source. We're going to run some current in there, so I can get two forces, again no net force but a torque, and I can kind of spin this shaft. How fast I spin it is going to depend on how much voltage I have. So really a practical application of this forces caused by current carrying wires and magnetic fields. A very cool and useful instrument that actually I used a little bit at NASA was called a mass spectrometer, or a mass spec for short. Essentially it measures the masses of atoms. It also tells you something about the chemical composition of an atom that you put into a mass spectrometer. What it really depends on is kind of a velocity selection. What we do is we're going to take a charged particle and we're going to put it into an electric field and a magnetic field, kind of like I've drawn down here, and we have it moving at some velocity. Now if you remember that force is going to be equal to charge times electric field, we also know that force is going to be equal to charge times velocity times magnetic field. These forces are going to balance each other out if the particle is not deflected as it moves through this region with both fields. So kind of what we do is we set these two guys equal to each other, cancel out the charge, and say, hey, we can meet this velocity criteria only when we're looking at speeds which are the electric field divided by the magnetic field. So here's kind of what we do is we take our sample and we charge it up and we run it through this region that essentially selects the velocity and says I'm only going to pass objects with a certain velocity into this magnetic field. Now these samples are going to curve, kind of like I showed earlier, but really how much they curve is going to depend strictly on their mass. So kind of heavier objects are going to impact down here, and maybe lighter objects are going to impact over here. So where we impact on this screen is going to tell us something about the mass or the composition of the sample that I passed through it. Pretty nifty if you're trying to determine what type of pollution we're looking at, which is kind of what I was doing at NASA. Now, you may have wondered, why can some metals become magnetized, such as iron and nickel, and others cannot, such as stainless steel and aluminum. To do that, what we kind of do is say we're going to break an object up into tiny little slices and say we're going to look at these things called domains. And I'll show you an example on the next slide. Now, these little tiny domains of a bar are going to kind of behave like a magnet. We're going to say that this domain is going to be pointing in that direction with some magnetic field strength. Same with that domain, same with this domain, and same with this domain. And you can kind of see in this bar right here, they're pretty much randomly oriented. And so we're essentially not going to have a magnet here. What we can do is we can say, put in a magnetic field and say how well do these magnetic domains line up with that magnetic field. So imagine if I had something like a piece of iron and I put it in a magnetic field, then all of these domains are suddenly going to point in the same direction, and we're going to have something that is very magnetic. If we put in a magnetic field and these domains are strongly locked in and they don't actually line up with a magnetic field, then we're going to have something that's not going to respond to a magnet, such as aluminum. As usual, I'll finish off my summary by just paging through the slides.